Okay, folks, so I'm going to try this again. I just did a screencast with the microphone turned off, which is too bad. So I'm going to have to redo this. I guess we can all laugh. I'm doing problem 7.38 as an example to complement the examples that were given out in your homework. And this is a problem involving the electron and muon, which are scattering in the center of mass frame. And we're taking this in the high energy regime where we can take the masses to be zero, i.e. the rest mass is going to be much smaller than the kinetic component of the relativistic energy. So we want to find the spin averaged amplitude. And again, for part B of this problem, to finish off the problem would be then to calculate once and for all the differential scattering cross-section and get a nice final answer. So again, this is really similar to what we've done before. Let's start off by just drawing a picture of what we're looking at. So in the center of mass frame, we've got the electron coming in. It's got form momentum P1, and again, we've got the muon coming in, and it's got form momentum P2, and this is before. And then after, what do we got? Take the electron to be scattering off at some angle here. Let's say that's theta. So this is the electron coming off. Call that P3. Okay, and then again, scattering in the center of mass frame has this nice, makes life easier for doing our calculations. Okay, so that's all we have, fairly straightforward. I think it's worthwhile maybe now, let's just write down our four momenta so that we can bookkeep all this, and then we'll consider a few important quantities that we're going to need for our spin average calculation. So starting off, so P1, the four momenta for the electron, of course it's got the time or zeroth component is just E over C, and we'll say that the initial momenta for the electron is Pi, okay? And so therefore obviously P2, again, this is elastic scattering, okay, in the center of mass frame, so energy is conserved, and we'll say that, and the momenta, therefore, of our muon is equal and opposite to that of the electron, okay, so that's before, and then after we've got P3, which again, energy is conserved. We've got total energy would be E. And we'll say that the final momentum, we'll call it PF. And of course, again, center of mass frame, conveniently we can write the momenta of our muon, therefore to be minus PF, okay? So that gets some of our quantities out of the way. Now, in terms of invariance, it's worthwhile to look at, for example, well, we're going to want to evaluate things like P1 and P2, but before we do that, let's consider a few other important results. First of all, based on the geometry, and again, because we're in the high energy limit, again, the relativistic energy expression that we have for the energy is trivially Pi squared, because these are kind of like photons now, even if they're fermions and the photon's a boson. And I'll be careful to put arrows over these. This is a physical momenta, and of course, okay, by the geometry as well, we note that therefore that we also have that important result that's based on the geometry as given in the picture above. Okay, so now let's go ahead and calculate some of these important inner products for 4 momentum. So P1 dotted with P2, we've got E squared all over C squared. Now be careful because remember that the P2 is opposite in direction, equal magnitude, but opposite in direction, so we have a negative sign. And whenever we're doing the dot products for our 4 momenta, remember, because we're in Minkowski space, the spatial piece gets a negative sign, so we have 2 negative signs, so that gives us a positive sign. Be careful for getting the right bookkeeping on that. So that's pi squared, all right? And then, again, of course, because, as I said before, in terms of the invariance here that we're looking at, this is just going to be equal to therefore 2e squared over c squared. In other words, as I showed the dot product just a moment ago, pi squared is equal to e squared over c squared. So we just have, therefore, the trivial result that's equal to 2e squared c squared. And note that, well, this is exactly the same. P1 dotted with P2, therefore, is exactly the same as P3 dotted with P4. Okay, because of momentum conservation and energy conservation. So that takes care of those two terms. Now we're gonna need to deal with P1 dotted with P4 as well. And so what does that equal to? So in terms of the components, looking at our 4 momenta, now we've got to be careful that we've got a plus sign again, because we've got pi for particle 1, which is the electron. But for P4, that's minus PF. So again, we get another switch in sign. Just be careful of that bookkeeping. But I just showed what pi dot with PF is just equal to, of course, e squared over c squared cosine theta. So this then is nothing other than 1 plus cosine theta. Okay. Now it's gonna be convenient for us, and I'll show it in a moment, but it's gonna be convenient for us to use some trig identities here. Let me rewrite this as cosine squared theta over 2, okay? Because that's going to be making our final expression, I think, a little bit easier for what you'll see in a moment. And of course, P1 dotted with P4 is again identically equal to P2 dotted with P3 for the same reasons discussed before. All right. Now that would seem to would appear that we have most of the quantities that we need. I'm going to also work out P1 dotted with P3 because we're going to need that. Why? Well, let's take a look at let me just work it out, and then I'll explain why we're going to need to deal with that. So again, just doing the mechanics of this. So this is e squared over c squared. Here we do get a minus sign because P1, or the physical momentum for particle 1, the electron, is positive, and for P3 it's also positive. So that's why the negative sign here comes because of the sign convention in Minkowski space. And so again, just be careful of the signs. And we can write out, again, this is just e squared over c squared. Now be careful that this is equal to 1 minus cosine theta. And using my trig subs, that's nothing other than I can write this as as 2 times sine squared theta over 2. Actually, I'm looking back here, and I apologize because I think I may have dropped a factor of 2. I'm putting it back over here, so you can see that if you take a look above, that should be, our previous expression should also have had a factor of 2, just from the trig identities, okay? So why did I worry about P1 dotted with P3. Well, if I go back to the expression that we were told to start with, and that was 7.129, okay, which was in our chapter here. We'd work this out in lecture. What I'm going to do is go back to equation 7.29, but substitute in that the masses are all 0, okay? So that the expression that I'm working with, So the expression that I'm working with is so this is equal to 4GE to the 4th all over P1 minus P3 to the power 4 times, and that would all be multiplied by, again, P1 dotted with P2, P3 dotted with P4, plus P1 dotted with P4, and P2 dotted with P3, okay? And we get this expression from evaluating the traces, which you can see in the notes. We did all that work already. Now we're just working with this expression. So what I want to focus on here is on P1 minus P3 to the 4th, which we can write as P1 minus P3 squared, all squared. And so if I look at P1 minus P3 squared, well, that's just P1 squared plus P3 squared minus 2 P1 dotted with P3. Be careful, that's the 4 momenta, right? But we know from the invariance that P1 squared is equal to m squared c to the 4th, so that's 0. And P3 squared, same thing, that's 0, because we're in the high energy limit here. And so therefore, P1 minus P3 to the 4th, therefore, is equal to 4 times P1 dotted with P3 squared. And we just worked that out above. That was just equal to, so P1 dotted with P3 was just equal to, so we have 2e squared over c squared, sine squared theta over 2, and that's all, everything there is squared. So then now we can start plugging in our results from above. So just our spin average then becomes the following. And I think I apologize because I think this term here, this was an 8. Sorry, guys. So if you go back to my expression above, I think I took the wrong result from 7.129. So there should be an 8 there. Okay, so but now when I put all substitute everything in, the 8 in the numerator, for example, will cancel with the 4 in the denominator here. That's going to give me a 2g e to the 4th. And that's all divided by, now I've got the stuff in it's all squared in brackets. So that's going to give me 4e all over c to the 4th now, okay, times sine 4 theta over 2. And then in my square brackets, I have 4e to the 4th all over c to the 4th plus 4e to the 4 over c to the 4 times cosine. Okay, and then factoring out the energy and doing some division. So factoring out the 4e to the 4th to the c, divided by c4, we've got 2ge to the 4th, okay, times 1 plus cosine 4 theta over 2, all divided by sine 4 theta over 2. So we have a nice relatively compact expression for the spin averaged amplitude. So now so that's part A, okay? So now for part B, we want to calculate the differential scattering cross-section. So if you go back to the expression that we had worked out in lecture, in our notes, the expression that we had worked out is equation 6.47 for muon electron scattering. So this was the differential scattering cross-section. We hadn't worked out the amplitude yet, but this was a generic. Actually, this was, pardon me, it wasn't limited to muon electron scattering. This was sort of a generic one for two particle scattering in the center of mass frame. Okay, so that's the outgoing final momentum over the ingoing initial momentum. So we're going to use this expression here, okay? Now, in this case, the statistical weight is trivial. S is equal to 1 because we don't have more than one unique particle, so we just have an electron and the muons. So the combinatorics are straightforward. And as well, because this is elastic scattering, again, Pi is just equal to Pf. The momentum is conserved, and the total energy is also conserved. And so in this case, the differential scattering cross-section is relatively straightforward, and just plugging in our results from part A with this formula, we get this nice form here. Here's the interaction strength. Again, this electromagnetic interaction. And the geometric factor then can be, if you will, isolated in this way. I don't know if that really helps so much with the trigonometric manipulations, but I think it's a little bit more compact. We'll stick with that. Maybe, one could ask oneself, right, with this particular situation, what happens if the scattering, how do you maximize the differential scattering cross-section based on the geometry? Or how is it affected by the geometry? But that's all that we're going to talk about for now. Hope that helps, and if you have any questions, please feel free to give me a shout.